right, so section 16.8 is going to deal with the sum and difference identities of sine and cosine. And you're going to get 4 new identities that you're going to have to work with this time. So let's talk about the sum and difference identities for cosine. We're going to introduce the variables alpha and beta, Greek letters, and they're just going to represent different angle measures. So if I wanted to take the cosine of 2 angles that I'm subtracting, I could expand that out as the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. And likewise, you can see that the sum identity for cosine is almost exactly identical as the difference. The only thing that changed was the plus sign turned to a minus sign. Okay, so somehow you're going to have to memorize that pair of identities. And so then let's take a look at the sine identities. So the difference identity for sine, we're now taking the sine of alpha times the cosine of beta minus the cosine of alpha times the sine of beta. So whatever it is that you need to do to get these 4 identities straight in your head and don't get them mixed up, make sure you do those. This is just a link that if you were in class, you would get to see a little video, but you're not. So here we go, moving on. So how would we use these identities? The cosine of 15 degrees, well, 15 degrees is not on our unit circle. And if we needed to actually get the exact value of the cosine of 15 degrees, and we didn't have a calculator, and all we had was, say, the unit circle, this is where your difference identity would come in handy. Because we can write 15 degrees as the difference between 45 and 30. So I can say this is actually the cosine of 45 degrees minus 30 degrees. And now 45 degrees is alpha and 30 degrees is beta, and I can just plug that into my formula, or my identity. So the cosine of 45 times the cosine of 30 plus the sine of 45 times the sine of 30. And then you just look at your handy dandy unit circle and you plug in the appropriate values for these 4 trig functions. So we have the cosine of 45 is root 2 over 2, cosine of 30 is root 3 over 2, the sine of 45 is also root 2 over 2, and then the sine of 30 is 1/2. So once we've plugged those in, now we just have to simplify. So if we multiply these together, we're going to get root 6 over 4. Multiply those together, we get root 2 over 4. And if we really wanted to be particular, we could combine it and make it 1 fraction. And sometimes people like to factor out the 1/4. It's really up to you. Okay, let's try another one. What about the cosine of theta plus 30 degrees? Now, our answer is going to end up having theta in it since we don't know what that actual angle measure is, so we can't evaluate it, right? But we can still apply our sum identity for cosine, and we get cosine of theta times the cosine of 30 minus the sine of theta times the sine of 30. We can evaluate cosine of 30 and the sine of 30 very easily. We plug those in, and then just to simplify, I can pull out the 1/2, and I'm left with the square root of 3 times the cosine of theta, and then minus sine theta. And I do like to move this square root of 3 in front so it doesn't look like that square root of 3 is being multiplied to the angle. It just makes it simpler to read. Okay, another example. We can do proofs with these identities. Thought we were done, huh? Nope. Okay, so just like before, we'll draw our bar. I'm going to use my sine identity over here. Can't really do anything on the right-hand side. So if I apply the sine, the difference identity for sine, I get sine of theta times the cosine of 90 minus the cosine of theta times the sine of 90. Well, if you remember either from graphing or from the unit circle, the cosine of 90 is 0 and the sine of 90 is 1. So when I plug those in, this goes away, becomes 0, and this is just negative cosine theta. So we're done. Yay! All right, last example. These types of problems where they actually give you an equation like the tangent of alpha is equal to 4 over 3 and the cosine of beta is 12 over 13. They're not telling us what alpha and beta are, but they're giving us these ratios for us to work with. On top of that, they're also telling us exactly which quadrant alpha and beta are going to be in. So the very first thing that we're going to do is draw our triangle in the first quadrant for alpha and plug in the appropriate values with opposite over adjacent, and then use our 3, 4, 5 triangle, so we now know that the hypotenuse is 5. We're going to do the same thing for beta, and if beta is between 3 pi over 2 and 2 pi, that's going to put us down there in the fourth quadrant. And then we plug in the 12 and the 13 for the cosine of beta, so that's adjacent and hypotenuse. And hopefully you recognize the 5, 12, 13 triangle, so that's a -5. Don't forget the minus sign. Okay, that's really important. And now we are ready to evaluate the cosine of alpha plus beta. So when they ask us for the cosine of alpha, we're going to look at alpha and read off what the cosine is. That's 3 over 5. And when they ask us for the cosine of beta, we go over here and we look at what's the cosine of beta. It's 12 over 13. So you can just plug in the appropriate values. The sine of alpha is 4 over 5. And here is the sine of beta, which is -5 over 13. And now we just simplify this. Okay, so we multiply it out, we get 36 over 65 plus 20 over 65. Add it together, we get 56 over 65. And we were able to do that all without a calculator and without even needing to know what alpha and beta are. All right, so if you guys are interested in learning about where these identities come from, how to derive them, I do have slides, but I didn't want to put that into the video and make it extremely long. So if you're curious, let me know and I will give that information to you. Okay, that's it.